Hey guys, so I wanted to talk about the Pythagorean identity for um, sine and cosine. So first I want to talk about what the Pythagorean identity is, and then I want to talk about how you would solve this problem using Pythagorean identity, and then how you could solve it without using Pythagorean identity. And then I'll let you decide which one you want to do. But first of all, the Pythagorean identity says that, says that the sine of an angle squared plus the cosine of the same angle squared equals 1. So that is an identity that we have for sine and cosine. You can see the proof here. Basically, it comes from we've been using the unit circle. It comes from the unit circle, right? I have the unit circle, the radius is 1, and I can make a right triangle. So I have y is sine and x is cosine. So sine squared plus cosine squared equals 1 squared, and 1 squared is just 1. So you don't even need to watch the proof video. That's the proof right there. That's basically why this is true. It's all based on the unit circle. If you didn't understand that very rapid explanation, go ahead and watch the video. All right. Anyway, let's talk about how I would use this to solve this question. So it says the angle theta 1 is located in quadrant 1. The cosine of theta 1 is 10 over 7. What is the sine of theta 1? So I can just plug this into my equation. Sine squared theta plus 10 over 17 squared, right? That's my cosine, equals 1. Sine squared theta plus 100 over, what's 17 squared? Not something I use every day. 289 equals 1. Sine squared theta equals 1 minus 100 over 289. Common denominators, that would be 289 minus 100 over 289. So sine squared theta equals 189 over 289. 289 is still 17 squared. So this is still, so the denominator is 17 squared. Let's figure out what the numerator is. This is sine squared. So I want to get this in terms of something squared over something squared. So I'm going to take the square root of 189. And it's not an exact value, but we do want an exact value. So I'm going to write it as a square root. But before I do that, I want to see if I can simplify it at all. I can. Okay. Yeah. Okay, so 189 is 9 times 21. 9 is a perfect square, so I can pull it out of the square root. So that's 3 square root of 21 squared. All right, so sine, right, this is sine squared. So sine equals 3 root 21 over, so sine theta, over 17. The denominators should match, by the way. The denominators of sine and cosine should match, and you'll see why when I explain the other way of solving this. But first, let's check our answer. So we're just gonna 3 root 21 divided by 17. Good, okay. So now that we know that we have the right answer, let's find it the other way and compare. So with this way, with Pythagorean identity, we just plugged in what they gave us and solved for sine. That was really all we did. Hopefully that's pretty straightforward. With the way we're going to do it now, we don't need the Pythagorean identity. We're just going to do it kind of our own way. Notice that everything in the Pythagorean identity is squared, though, so we lose positives or negatives. That's why they told us that it was in quadrant 1. So if this had been in quadrant 4 and we were given this, then we would have known that sine had to be negative. So we would have done the exact same thing and then just said, oh, but it's negative because it's in quadrant 4. This was in quadrant 1, so I wasn't worrying about that. But when you're in any other quadrant, you need to make sure that you're paying attention to your signs. So this couldn't have been in quadrants 2 or 3 because cosine would be negative. So if they gave us a negative number here, then it could have been in quadrant 2 or 3, and then we would have had to pay attention to what sine was in either of those quadrants. So yeah, so that's why they tell you the quadrant, so that you can figure out what the sine is. And again, that would be using All Students Take Calculus, that acronym, to figure out what the signs are. So they aren't just telling you quadrant 1 for no reason. They're telling you so that you know positive, negative. Okay. Let's look at the other way of solving this. So we're in quadrant 1, so I'm going to draw my triangle in quadrant 1. I know that cosine is adjacent over hypotenuse. Adjacent over hypotenuse. So 10 must be the adjacent. So that's x. Adjacent is x. And then hypotenuse is going to be here, 17. So I can figure out what this other leg should be by using the Pythagorean theorem. So instead of using the Pythagorean identity for sine and cosine, I'm using the Pythagorean theorem, which is where the Pythagorean identity comes from, but we're more familiar with the Pythagorean theorem, obviously. So I have 17 squared equals 10 squared plus, let's call this b squared. Okay, so 17 squared is 289. We did that earlier. Equals 100 plus b squared. Subtract 100 from both sides. 189 equals b squared. This should be looking very familiar because these are the same numbers we were working with in the last way we did it. Square root of both sides. Simplify to get 3 square roots of 21 equals b. So then sine is opposite over hypotenuse, so that's going to be 3 root 21 over 17, which is exactly what we got before. So this is just another way of doing it. Do whichever one works better for you. I know that the point of this is to get you used to using the Pythagorean identity, but honestly, This is my go-to way of doing it. This is what makes logical sense in my head because I don't have to remember a formula. I'm just drawing a triangle and then using what I know about right triangles, which I guess I have the Pythagorean theorem memorized, but that's one that is already memorized. I didn't have to memorize a new one just for this type of problem, right? This is a Pythagorean theorem is something that we've been using forever, well, since geometry. But the point is, like, that's something that's already in our heads. So I like this way better. If you want to use this, by all means, go ahead. This identity is very much a good thing to know, and you will be using it a lot in pre-calc, in the trig section of pre-calc. But for this type of problem, I think it's more intuitive to use this way of solving it, but that's up to you. Okay, let's go on and see if I want to, yeah. Let's do this one because it's in a different quadrant, and so I want to talk about that. So I'm going to do it both ways again. Yeah. So, yeah. Let's just do it. Okay, so we're given cosine again. They could give us sine and ask for cosine, but they didn't. So 9 squared over 19 squared equals 1. I'm going to go ahead and subtract it to the other side while expanding it. So 81 over 19 squared. $361. Okay. And then find a common denominator. So 361 minus 81 over 361. 361 minus 81 is 280. 361. Okay, so now we need the square root of 280, which again is not a nice number, so let's try seeing if we can simplify it. Okay, so it simplifies down to 9 times 70. So that's as simplified as it gets, is 9 times 70. Sorry for that pause there. So 9, what am I doing? 9 times 70, so the square root of 9 times 70 is 3 square roots of 70 over, and then we know that 361 is 19 squared. So that's sine squared. So sine is 3 square roots of 70 over 19. Okay, so that is the Pythagorean identity version. So now let's do the drawing the triangle version. Oh, wait, what did I miss? I missed the fact that it's in quadrant 4. It's in quadrant 4. So like I said last time, if you have a positive cosine, you could be in quadrant 1 or 4. And in quadrant 4, sine is negative. So we're told we're in quadrant 4, so sine is negative. So I have to go in and add that at the end. So if I use Pythagorean identity, I have to go in at the end and say, oh yeah, what quadrant am I in? Let's make sure my signs are correct. That is one of the things that the method, the other method, the triangle method, does better than the Pythagorean identity method, and I'll show you why. So I'm going to go ahead and draw it in quadrant 4. So I'm going to pay attention to the fact that it was in quadrant 4 at the beginning instead of the end. I feel like it's easier. I'm drawing a picture. I'm trying to think about where things are going to go in my picture. That's when I think about the fact that it's in quadrant 4, not at the very end when I'm like, oh, I'm done. And then I forget to think about what quadrant it's in. Sorry, it's really hard to get things straight. I'm going to start over. Wow, okay. All right, so here's my triangle. It's in quadrant 4. I know that cosine is adjacent over hypotenuse, or the x distance over the hypotenuse. And then I can see that y is in the negative direction. So when I label this, it needs to be negative because y is negative in this direction, right? So I'm going to use my Pythagorean theorem. So I have 19 squared equals 9 squared plus, I'm just going to use b again, b squared. So I'm going to subtract 9 squared from both sides. So again, this is 361 minus 9 squared is 81 equals b squared. So that's 280 equals b squared. So that's 3 square roots of 70, because we already figured that out, equals b. Okay, so then when I put that here, I'm like, oh, okay, that must be negative because it's going down, right? This is going down, so y is negative here. And I can think about the fact that I'm taking the square root of both sides, which is plus or minus, which forces me to make a decision between plus or minus. So this is going to be minus. So I would look at my picture and say, oh, okay, that must be minus because I put it's in quadrant 4. So y is negative, so it's minus. I just feel like it's more intuitive when you're looking at the picture. Say, oh, okay, now I know it's negative. I don't have to think at the very end, okay, I'm in quadrant 4. All students take calculus. Cosine's positive, which means sine is negative. Like, that's like the whole thing that has to go through your head at the end. If you do it the other way, if you do it this way, you've already got a picture that's showing you that y is negative and y corresponds with sine. So, yeah. So then we get the same answer that we got in the first place. Okay, so hopefully that helps. Let me know if you have any questions, and I will see you later.